You know that feeling when you look at the world and it just seems like one giant, incredible puzzle? A mystery just sitting there waiting for someone to solve it. Well, today we're going to do just that. We're cracking the code. We're opening up the powerful toolkit that helps us make sense of, well, everything.
I mean, it's the biggest question there is, right? From why the sky is blue to how life even got started. How in the world do we find real, solid answers to these endless questions? It can feel a little overwhelming. But it turns out there's a system for it, a method.
Okay, so for the next few minutes, I want you to put on your detective hat. The entire universe, that's your crime scene. It is absolutely full of clues, hidden truths, and strange little details. And every single great detective needs a reliable set of tools to solve the case.
So, what's in this toolkit? Let me tell you, it is not some boring list of rules from a dusty old textbook. Nope. It's a powerful, dynamic framework for thinking clearly and discovering how things actually work. This is the scientific method.
So let's pop this toolkit open. You'll see it's really a cycle, and honestly, it can get a little messy sometimes. It all kicks off with a clue, some weird observation that makes you stop and ask a question. Then you form a theory, like your first hunch. After that, you've got to design a way to test that hunch, and finally, you look at the evidence. This is how detectives and scientists go from, I wonder, to, aha, I know.
Let's zero in on that second step, the hypothesis. This isn't just a random shot in the dark. Not at all. It's a very specific, testable prediction. It's the detective in the story saying, my hunch is the butler did it, and here is exactly how I'm going to prove it. It has to be something you can actually test.
And this part right here is absolutely crucial. To get reliable evidence, the kind of evidence that would actually hold up in court, your test has to be fair. You can't just do whatever you feel like. You have to design an experiment that perfectly isolates the one thing you're trying to measure. So how do we do that? Well, it really boils down to two key players. First, you've got the independent variable. Just think of this as the one clue you're putting to the test, the one and only thing you change on purpose. Then you have the dependent variable. That's what you measure to see if your change had any effect. A super easy way to remember it is, I change the independent variable, and what I observe depends on that change. Now, to make sure it's a fair test, literally everything else has to stay exactly the same. We call these your control variables. Think of it like keeping the crime scene clean. So if you're testing a new fertilizer on a plant, you can't also give that same plant more sunlight and extra water. Why not? Because then you'd have no idea if the plant grew because of your fancy fertilizer or just because it got more sun.
All right, toolkit in hand, let's go tackle our first big case. And we're going big with this one. We're going to try to crack the code on one of the oldest mysteries there is. What is everything actually made of?
Okay, clue number one. A huge breakthrough discovered over centuries of investigation is this. Everything you can touch, taste, or see is made of these unimaginably tiny building blocks called atoms. Your phone, the air you're breathing, the stars in the sky, it's all atoms.
But here's the thing. Not all atoms are the same. Each type of atom, what we call an element, has its own unique ID card. This is its atomic number, which is simply the number of protons it has in its core. 1 proton, that's hydrogen. 8 protons, you've got oxygen. It's a one-of-a-kind fingerprint.
And this brings us to the detective's master list of suspects, the periodic table. This chart organizes all the fundamental ingredients of the entire universe. So, for example, as you can see here, an atomic number of 1 always means you're dealing with hydrogen. An atomic number of 6 is always carbon, and 8 is always oxygen. Every single element has its own unchangeable code.
Now, this is where things get really cool. When these ingredients start to interact with each other. We call it a chemical reaction. And in a reaction, atoms aren't created or destroyed, they're simply rearranged to form completely new things. It's kind of like taking the same pile of Lego bricks you used to build a house and taking them apart to build a car instead. Same pieces, new creation.
And that leads to this huge, fundamental rule in science. It means that in any reaction, the total amount of stuff you start with is the exact same amount you end with. The atoms just get shuffled around into new partnerships. For a detective, this is massive. It means no piece of evidence ever truly disappears. It just changes form.
So how does all of this theory play out in a real-world case? Well, let's look at the amazing work of Alexander Fleming, a true detective of biology, who used this exact toolkit to stumble upon a clue that would change medicine forever. The whole investigation started with just a simple observation. Fleming got back from vacation and found that one of his lab dishes of bacteria was contaminated with mold. Gross. But then he noticed something really weird. Right around the mold, there was this clear zone where the bacteria just weren't growing at all. So he asked the most important question anyone can ask.
Why?
He didn't just shrug his shoulders and throw the contaminated dish away. No way. He formed a hypothesis, a smart, testable guess. He proposed that the mold itself must be producing some kind of substance, a sort of mold juice that was killing the bacteria around it.
And then he did what any good detective would do. He designed a fair experiment to test his hunch. First, he isolated that specific mold. Then he grew a whole bunch of it in a liquid broth to make a lot of that mold juice. That juice was his independent variable. He then applied it to all sorts of different bacteria and carefully observed the dependent variable. Did the bacteria die?
And the result? Well, it literally changed the world. His hypothesis was spot on. That mold juice contained what we now know as penicillin, the world's very first antibiotic. This wasn't magic, and it wasn't just blind luck. It was the direct result of a curious observation followed by a structured, methodical investigation.
And this brings us to the most important point of all. This incredibly powerful toolkit, it's not locked away in some fancy lab for famous scientists. It belongs to you. It's a way of thinking, a way of looking at the world that anyone, and I mean anyone, can use.
Because at the end of the day, that's what science really is. It's not about memorizing a bunch of facts for a test. It's about being curious. It's a process for asking good questions and a reliable method for finding the answers. It's the spirit of the detective, and it's alive in all of us. So as you go about your day, keep your eyes open. Start looking for the little puzzles and strange clues the world leaves behind for you. Because now you have the toolkit. The only question left is, what mystery will you solve first?